Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. Okay, we meet again in continuation towards the previous video, SIRI number 1. This is frame analysis using moment distribution method. Okay, so in the first series, we have discussed about actually this question. This is sidesway frame, and I have explained how we actually derive the final formula to calculate member and moment for sidesway frame, because we have to consider two parts of analysis. We have to have the table. We calculate FEM due to external loading only, and we have to have another table because we cannot combine the FEM. FEM due to sidesway is unknown, so we actually assume the FEM for sidesway, and then we do table number 2, and at the end of analysis we find the correction factor. And that's how we get the value, the end moment, the member end moment for frame with sidesway. And I have actually summarized the procedure for analyzing frame with sidesway, okay, using 4 steps. Okay, step number 1, we will start with calculating stiffness factor and distribution factor. Of course, this distribution factor will be used in both table number 1 and table number 2. For step number 2, we analyze first the non-sway frame. For the non-sway frame, actually we consider only external loading to calculate the first moment in the table, and then after we finish distribute moment, we use all the member and moment that we get from the table, and we should do the static analysis in order to determine the restraining force. Then we move to step number 3. In step number 3, it is sidesway frame. In sidesway frame, we actually assume FEM due to delta, and then we will calculate FEM for another member, and we basically use trigonometry and interpolation in order to do that. Then we calculate the end moment in table number 2, and we label as M prime. Okay, and after that we have to calculate the restraining force R prime. So in this step, this is the same process like what we should do under the table number 1. Also we need to find the R value, the restraining force, but that one is R, restraining force R, and for the table number 2, it is restraining force R prime. So this R and R prime actually give us the correction factor. Finally, we combine all the known that we calculated. Okay, in one formula, it is the formula to calculate final end moment for the sidesway frame given in the question. It is M naught. M naught is the end moment from table number 1 plus correction factor. Correction factor is R divided by R prime. We times with member and moment from table number 2. Okay, once we have all the final end moment for 6n, because we have 3 members, so we have 6n. Then we can use the moment that we get to draw the shear force diagram and the bending moment diagram. Okay, let's start now. We will start with the first step, calculating stiffness factor and distribution factor. Okay, so in order to do that, I will copy this and put in Excel because I want to calculate the member and moment in Excel, because this moment distribution method is actually one of the famous method in the world. To whenever we want to do design, we use moment distribution method. Okay, so let's start now. So now I move to Excel. Okay, so I have actually list all n moments. We have 3 members and we have 6 n. We have NA for AB, we have NB for BABC, and we have NC for CBCD, and we have ND for DC. So the total is 6. So we have to have 6 column for that. We will produce 6 member and moment. Okay, K and distribution factor I put directly in the table. So K is in terms of EI. Doesn't matter because EI will be cancelled whenever we calculate distribution factor. And the length for each member in this case, in this frame, is equal. It's all 5 meter. It's all 5 meter. And since A and D fixed support. A and D is fixed support. So we just need to use 4 EI over L for all members. So it is 4 EI divided by L. L is 5 meter. So we get all 0.8. We get all 0.8 for AB, for BC, and for CD. 0.8 for all. Okay. We get all 0.8. Actually, we only have three value of K, because K is for the element, K is for the member. Okay. And moment we have 6, but member we have 3. So we share the same value for AB and BA because it is the same. Okay. We have all 0.8 because EI is constant, length also constant. Actually, if you don't want, you don't need to put K in the table. Start with distribution factor. Okay, so distribution factor for fixed N is 0. For pin N, for N pin is 1, and fixed is 0. And fixed is 0, and pin is 1. So now we have 2, and fixed at A and at D. So we have to use 0. Okay, rigid joint B and C is rigid joint. So internal joint we have to assume as fixed. Internal joint, including rigid joint, has the same characteristic with roller and pin. Internal roller and pin. Okay, for beam. Okay. So having this, we will get all 0.5 for the factor. Okay, for the factor we will get all 0.5. So be careful whenever you calculate distribution factor, because it always depend on the length, the E and the I. Okay, if one of these is not constant, then you will get different value. Okay, so the first value in the table, so this is table number 1. This is table number 1. Always remember that in table number 1, okay, back to this first. Okay, in table number 1, we are referring to this. Okay, step number 2 here. Okay, table number 1. It is non-sidesway frame. It is non-sidesway frame. So the diagram for this will be like this. We have one pin. This is 16. Okay. This is 16. One pin. And we have R here. Okay, so this is the diagram for step number 2. It is non-sidesway frame because of the support that we put at C. Okay, so this is the one that we analyze in table number 1. Table number 1. So based on this diagram, we have FEM, which is come from member BC only. Member BC only. We have 1 meter and 4 meter. This is 1 meter and 4 meter. 1 meter and 4 meters. So we calculate the FEM by referring to the appendix given. Okay, by referring to the appendix given. Okay, move back to Excel. Okay, so FEM, okay, this is FEM due to loading. This is table number 1. Okay, so we have FEM for member BC. One is negative, one is positive because FEM is behavior. Okay, FEM is behavior. So the moment will push back the N and B and C to straight position because due to loading the band will bend. The beam will bend. So we have to apply moment. Okay, moment to counter back. So FEM is behavior. So we have to consider the behavior whenever we want to analyze, means that we have to put sign representing behavior. Okay, so one is negative, one is positive. So BC is negative, CB is positive because we compare the behavior, okay, the moment with the sign convention. Okay, so it is 16. It is 16 times, okay, refer the formula. It is 4 times 4, 4 square. 4 times 4 times 1 divide by L square. L square is 25. L square is 25. So we get 10.24. I need to put negative. Okay, don't forget to put negative. It must be negative because of the behavior. Okay, and another one is positive. Another one is positive. It is 16 times 1 times 1. Please refer the formula. Times 4 divided by 25, 5 square. So this is equal to 2.56 positive. Okay, so as usual, like what we have done in beam analysis, the first step after we have putting the FEM as the first moment in the table. Okay, next step is distribution. Okay, we have to do distribution. Okay, and as I explained also, when we distribute moment, we don't distribute member and moment, but we distribute joint moment. Okay, so FEM, from FEM formula, we actually determine the first member and moment in the table. but the moment that we distribute is actually join moment, which is opposite with member and moment. Okay, so what we need to do is we have to find join moment. So join moment for B is BA plus BC, and opposite with negative 10 is positive 10. So that is why we get 10.24 as the join moment. We have to times with the distribution factor. Okay, so normally we change sign or we put negative to representing that behavior opposite condition. Okay, so it is 0 plus negative 10.24. So I have put negative, means that now we are actually doing determining join moment. Join moment. Okay, so it is 0 plus negative 0.24. We put negative to represent the join moment. So we times with distribution factor 0.5. Okay, we get positive 5.12. We get positive 5.12. So we do the same for BC. Of course, we will get the same because total is 10.24 times with 0.5. So we will get the same 5.12. Okay, so for member for joint C, we have C from CB and CD. Joint C, we have CB and CD. Okay, so we get one moment value, it is 2.56. That is member and moment. So that is why when we analyze, we have to put negative. Okay, we have to counter back because of the joint moment that we need whenever we distribute moment. Okay, so I put negative to represent the behavior. Okay, the behavior. So it is negative 256 as the join moment, not positive 2.56. Positive 2.56 is member and moment, but the moment that we distribute is join moment. Sorry. Okay, in the table, the value from fixed and moment is member and moment. But the moment that we distribute is the join moment. So that is why the join moment is negative 2.56. Okay, so it times with 0.5. Okay, 0.5, so we get negative 1.28 as well because the factor is equal. Okay, and then since all A and B are fixed end, so we have to carry the value by times with the factor, and the factor for n fixed and internal support is 0.5. If the n is n pin or n roller, the factor is 0. So in this case, the factor is 0.5 for all. 0.5 for all. So we have to bring the value to the opposite. Means that if we have the value from BA, we have to carry the value to AB. It is 5.12. It is 5.12. We divide by 2. And we have to do the same for BC because we need to carry the value to CB. It must cross boundary. B we have we have BA. This BA we have to carry to AB, and we also have BC, and this BC value we have to carry to CB, and we have to do for all. Okay, so it is negative. No, not negative. It is equal 5.12. We divide by 2. So what we get is 2.56. And at carryover at this level, we don't have to change the moment value. The moment value we change at distribution, not at carryover. Okay, so the value for CB, we have to carry to BC. So it is 1.28 divided by 2. And another one, we have value for CD, so we have to carry to D, so it is divide by 2. Okay, so it is for the carryover, so we actually doing this. Okay, this one we carry cross boundary, and then for BC we also carry, okay, we cross the boundary, and we have CB, we carry to BC. Okay, we carry to BC, and we have CD, we have to carry to DC. Remember, we are doing this because A and D are fixed. If not, we don't need to carry because the factor is 0. Okay, so this is the process for one cycle. So next step is we need to repeat the process. Okay, so for AB, since factor is 0, so the 2.56, actually the negative 2.56 we time with 0, so that is why we don't put anything. Okay, for B, join B, we have 0 and negative 0.64. We have 0 for BA, and we have negative 0.64. Okay, so what we do is, for distribution, I put negative because we have to change the direction. We have to change the direction to represent the behavior of joint moment. So it is 0 plus negative 0.64. So we actually get 0.64 positive. Okay, times with the distribution factor. So we get 0.32. 0.32 again. And then 1.56 put negative because we have to change sign. Okay, times with 0.5 because the factor for CB is also 0.5. So we get negative 1.28, and then we get the same. Because of the factor, okay, because of the distribution factor. If not, we have to calculate. Okay, carefully. Okay, next, continue back with carry over. The factor is 0.5. We have to divide by 2. Okay, each value, since all in this frame is fixed, including internal. Okay, including internal, so we just need to times with the factor. Okay, so it is 0.32 divided by 2. Okay, we carry the value to the opposite. Okay, it is 0.32 divided by 2. Okay, we have negative 1.28 that we need to carry to B. We need to carry to BC. So it become, okay, negative 1.28 divided by 2. 1.28 divided by 2. Okay, and then we have another 1.28 for CD. We need to carry to DC. Sorry, this is not negative. No need to change sign. So carry over, we don't change sign. Distribution, only we change sign. Okay. Okay, now repeat again for the next cycle, distribution. Okay, 0.16, because the distribution factor is 0, that is why we don't get anything here. Okay, and then we move to BA. So BA is come from joint B. So we have BA and BC as the joint moment. So we put negative so that it represents the joint moment, which is opposite with member and moment. So it is 0 plus 0.64. Okay, we have to times with the factor. The factor is 0.5. So we get negative 0.3 Okay, we do the same. We times with the factor. Okay, 0.64, we put negative, 0.64 times 5, and times with the factor. Okay, and then we carry again the value. We carry again the value, divide by 2. So this one divide by 2. Okay, and then, okay, remember to cross the boundary. Okay, and last value in this level, we divide by 2, the factor is 0.5. Okay, again, continue to the next distribution. Okay, continue to the next distribution. Okay, it is negative 0.064. Okay, times with distribution factor 0.5, we should get positive. We should get positive. Okay, again 0.6064 times with the factor 0.5. Okay, we also get 0.032. So that this 4 value, when we plus, we get 0. We get 0. Representing equilibrium condition for joint equilibrium. Okay, so this one negative 0.16 opposite, so it should be positive. Okay, we time with the factor 0.5. Okay, and again, this is distribution. We should change sign. 0.5. Okay, so let's look how many times that we distribute. 1, 2, 3, 4. Actually, you may stop whenever the value, the last distribution reaches 0. If you can get like this 0.0 something, actually you can stop. Okay, you can continue if you want, but you can also stop after you meet 0.0 something. Okay, so don't forget, we always need to stop at distribution, not carry over. Okay, so this is M naught, table number 1. This is M naught. So total of this will give us M naught and moment for non-side sway frame. Okay, so I want to find the total. Okay, the end moment we get from total moment in the table. Okay, this one I have to click. Okay, so we have 6 value, 6 end moment value. Okay, 6 end moment value from table number 1. From table number 1. Okay, from table number 1. Okay, let's continue. So now I want to copy this table and put back in Excel. Sorry, in OneNote. Okay. So this is the table. This is table number 1. Okay, so this is table number 1. Table number 1, we get M naught. Okay, it means that this is the moment that we get 2.56, 5.152 plus negative 5.152 equals 0 because MB is equal to 0. This is representing MB, which should equal to 0. And this should representing MC, which is also equal to 0 for the rigid joint. Okay, so this one is negative 3.2. So because of N fixed, if we analyze NP, so this has 0 value. This is N fixed, so we should get value for both A and D. Okay, we should get value for A and D. This is M for A, this is M for D. Okay, so now the next step is we have to calculate restraining force. Restraining force. So the important part here is we have to be able to draw. We have to be able to see the free body diagram of the non-side sway frame. For the non-side sway frame, this is the frame. So we have R here, we have 16 like this. Okay, now we have to complete this. Okay, with the free body diagram. The free body diagram. The moment, okay, we get positive for MA and we get negative for MD. Negative. Okay, so the value, this is 2.56 and 1.32. 1.32. 1.32. 2.56, 1.32. Okay, so the free body diagram of this is very important. So this is a free body diagram of non-side sway frame. So we determine M naught in table 1, okay, based on this diagram. Okay, so we label until the end. So this is AX, this is DX. Okay, and then we have A, Y, and D, Y. Remember, at this level, we are analyzing this to determine the restraining force value. Restraining force in horizontal component is a horizontal reaction, which we get from the support that we put, artificial support. So since we have to calculate R, so we have to have the equation with, we can relate R into the equation. So we have to have what we call as shear equation. Shear equation, because we are referring to the column. We are referring to the column. Column is horizontal member. Column is vertical member. Column is vertical member. So the delta for column is in horizontal direction. Horizontal direction. So, and the delta occur due to shear. So that is why we call it as shear equation. Okay, so we have to have the shear equation. So this is shear equation. Okay, the shear equation is total Fx is equal to 0. Shear equation. So from the shear equation, total Fx equals 0. Total Fx equals 0. So what we should do is we have to write an expression, an equation. Okay, based on total Fx is equal to 0, referring to the free body diagram. So from this, we can write like this. Ax minus dx minus r equals 0 because it is shear. we consider all horizontal forces. Okay, and R is actually equal to AX minus DX. R is actually equal to AX minus DX. R is equal to AX minus DX. So now our task now is to calculate what is AX value, what is DX value. Okay, if the first one is called as shear equation, if this is shear equation, okay, we will continue to get AX and DX by using one analysis that is called as column analysis. Means that when we want to calculate AX, we have to analyze column AB. When we want to analyze DX, we have to analyze column CD. Okay, remember that delta perpendicular with the element is column. That's why it is vertical. Column is vertical, delta is horizontal. Okay, so we have to calculate AX and DX using analysis that is called as column analysis. This is column analysis. We move to column analysis. Column analysis means that we have to analyze one by one column. We have to analyze column one by one column. Okay, let's say I move to here. Okay, we have column analysis. Column analysis. We have column analysis. So we have to analyze column AB. We have to analyze column AB. Moment, we have positive. Moment, we have positive. We have positive. Okay, we get 2.56 and 5.152. This is 2.56 and 5152. Here is 5152. This is 5 meter. And A, we have to refer to this direction. We cannot simply doing column analysis without diagram. We have to have the diagram because the process when we analyze AX and DX will be based on the diagram. Okay, so have the diagram first and then only you calculate the AX and DX. Okay, so AX in this direction, this is AX. Okay, so having this, can we determine AX by taking moment at B? Because we want AX, we take moment at B. Because we want to find AX, we have to take moment at B. So this is just like simple calculation, the one that you have learned previously. This is column, even though previously you learned how to calculate reaction for simply supported beam. Okay, actually we can apply that knowledge in analysis of column. Okay, we have to take moment at B. Okay, we take moment at B, So equal to 0. This is moment at B. Okay, clockwise, positive. Okay, clockwise positive. So it is 5.152 plus 2.56 minus 5 AX equals 0. So AX, we will get value here. Okay, this is column analysis. This is for AX. This is for AX, and we can continue to calculate, to analyze column CD using the same step. Okay, analyze the same CD using the same step. Okay, using the same step. So we have, okay, look at the moment. It is negative, negative. It is negative, 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 negative. And the dx is in this direction. So this is dx. Again, this is also 5 meter. 5 meter. So the value from the table 2.56 and 1.32. 256, 132. This is 256. This is 132. Okay, so we have to take moment at C so that we get dx. Okay, it is negative 2.56 minus 1.32 plus 5 dx equals 0. So dx. Okay, so once we have ax, once we have dx, so this ax and dx, we have to substitute into this one. We have to substitute into the shear equation. Okay, we have to substitute into the shear equation. Okay, substitute into the shear equation, then we get R value. Okay, this process will be repeated under table number 2, step number 3. Not 3 means 3. Table number 2. Next step after we have determined M prime. Okay. Okay, so I don't want to finish this because I want you to complete this. Okay, please calculate what is AX value. Please calculate what is DX value. So please calculate all this and substitute into the shear equation, then find or calculate the restraining force R. Okay, so I want to stop right now. This is series number 2. So in the next series, in series number 3, I will show to you how we are going to assume FEM for sidesway. FEM for sidesway, we focus on how we actually assume FEM, and then we calculate FEM for another column, because we only assume one column, one value from one column, and then using ratio we will find for another column or another member. So I stop right now series number 2. So for series number 3, please continue to watch because it is very important. I will show to you how we will analyze side sway frame using moment distribution method. Okay, thank you very much. Inshallah, we will meet again in series number 3. Okay, thank you. Assalamualaikum warahmatullahi wabarakatuh.